This is number 5 from the 2011 exam. Okay, so we're starting at 2010, and a landfill contains 1,400 tons of waste. And we've got the increasing function W models a total amount of waste stored at the landfill. Planners estimate that W will satisfy the differential equation, here's our differential equation, for the next 20 years. So they're talking about domain right here. W is in tons, T is in years, starting at 2010. Okay, so for part A, we are going to approximate the amount of solid waste that the landfill contains at the end of the first 3 months of 2010. And they were very nice. They told us that that is when T is equal to 1/4. So we need a tangent line. So let's start off with the slope. And we are using the tangent line at the graph of W at T equals 0. So the slope when T equals 0 is 1/25. When T equals 0, we know that we've got 1,400 tons of solid waste. So we end up with 1/25 times 1,100, which is 44. So that's the slope of our tangent line. So we're looking at y minus y1 equals the slope times x minus x1. Y minus, our y value is 1,400. Our slope is 44. Instead of x's, we're using t because t is time, so it's t minus 0. And if we solve for y, we get that y is 44t plus 1,400. So we're going to use our tangent line to approximate the value of w at 1/4. So that's about 44 times 1/4 plus 1,400, which is 1,411 tons. Okay, now part B. We get to find the second derivative in terms of W. Okay, so part B, I'm just going to write our function again, or our differential equation is 1/25 times W minus 300, so the second derivative. I'll use the constant multiple rule and leave that 1/25. Then we multiply by the derivative of W and negative 300. Now we know the derivative of negative 300 is 0, but the derivative of W is dW dt. And we know what dW dt is. dW dt is 1/25 times W minus 300. So here is our second derivative in terms of W. And the second part of our question, we have to determine if our answer to part A is an underestimate or an overestimate. And what they're getting at is concavity. So we need to know the concavity of our function. And to figure that out, we need to know if our second derivative is going to be positive or negative. So the information that we have here, let's see, is that W begins at 1,400 and W continues to increase. So the value for W must always be larger than 1,400. So if W is always larger than 1,400, then this quantity here will always be positive. And this positive value times this positive will be positive. So we can say our second derivative is positive. Therefore, W is concave up. And if our graph is concave up, then our tangent line is under our graph, which means that our answer is an underestimate. So W is concave up. Which means the answer, part A, is an underestimate. Okay, one more part. Part C, we are solving our differential equation. So dw dt let's separate our variables. So we'll have now you can put the constant to either side. Since I know we're ultimately solving for W, I'd rather have it to the right. We integrate both sides. This is going to be a natural log. Now we substitute our initial condition. They tell us that W is 1400 at t equals 0, which means that C is the natural log of 1100. So now we can exponentiate. We'll have W minus 300 is equal to, this will be e to the 1 over 25t times e to the ln of 1100. This simplifies to just be 1100. And now we have to decide what sign we're going to use, because we know our quantity could be positive or negative within the absolute value. But we know from our initial condition that if t is equal to 0, we need to get a positive 1400, and the only way we're going to do that is if our quantity is positive here. Which means that our solution is 1100 e to the 1 over 25t plus 300.